About my talk, and first about the title of my talk, especially the part Journey Behind Calculus. Because of my accent, probably, when people meet me here in the United States, their first question is, where are you from? And the second question is what you are doing. And when I'm telling that I'm teaching mathematics at university, they usually ask me, do you teach calculus? I say yes, but not calculus only. They say, so difficult. I said, okay, and difficult and other things. And they usually ask me, is there anything behind calculus and difficult in mathematics? And this is a very natural question, because when I thought about these questions, I understood some reasons to ask such questions. First of all, mathematics is probably the most conservative science to teach, because what we teach is at least 300 years old. I don't know any other science who teaches things which were finished 300 years ago. And also, if we look at what we teach, it's mostly calculus. So I will try to discuss the following questions today. Is there mathematics behind the calculus? And what kind of mathematics is behind calculus? Or what happens during the last 300 years? Do engineering students need mathematics, and how much? Of course, there's going to be no complete answers, just some kind of thoughts. If there is a mathematical problem, why not just ask a mathematician to solve it? So why do engineering people need mathematics when they can go to mathematicians and ask the answers? And finally, challenges of collaboration. We had some kind of teaching, some kind of event recently, and there were two ladies who presented some kind of thoughts about education. And they said that they asked in many universities, and what people mostly want in all universities, what they are looking for is collaboration. And so I will try somehow to explain why collaboration is so difficult. So the first question is, there is mathematics behind the calculus. Today, everybody studies calculus in high school, in college, everywhere. So calculus, everybody studies calculus. But actually, as a matter of fact, calculus is just a beginning of a very long way into mathematics. It's just entering gate rather than even the basement of mathematics. My first idea, crazy idea, was to make some kind of scheme which shows different parts of mathematics, but very soon I understood that it's impossible. It's even to list all areas of the modern mathematics, I will need at least 1 hour. So I just mentioned some kind of areas in mathematics which start with calculus. And calculus, ordinary differential equations, partial differential equations. Partial differential equations, from my point of view, is a central part of the mathematics, because it's the part which is mostly related to applications. You can see that partial differential equations have applications in physics, engineering, economics, control theory, and so on. And all these parts of mathematics are related to each other. So it's kind of a very complicated tree. Mathematics of the 20th century, or mostly probably the first half of 20th century, was strongly, one of the main areas of mathematics was partial differential equations, and mostly linear problems were considered. And it was very good progress in the partial differential equations. One of the main questions which appears when people think about mathematics, everybody knows that mathematics solves problems. And the question is which problems are good and which problems are bad. In the mid-50s of the last century, French mathematician Jacques Hadamard defined what is the well-posed problem. Okay, before I continue a little bit about collaboration of mathematics and other sciences. No surprise that the best way to collaborate with mathematics was found in physics, because physics is probably the science which is most closest to mathematics. And in physics, just to show how complicated is this collaboration, in physics everything starts with experimental physics. Experimental physicians, they find new phenomena. They have the direct contact with nature. They do experiments and they get the results of experiments. Then the results go to the theoretical physicists. Theoretical physicists try to understand and to explain these phenomena and try to get some formulas behind these phenomena. Try to explain them on some mathematical form. After that goes mathematical physics. Mathematical physicists, they are also called intuitive mathematicians. They are as much mathematicians as physicians. They understand both physics and mathematics. They do not construct rigorous proofs, but they build some mathematical theory under what theoretical physicists discover. After that, it goes to applied mathematics, and applied mathematicians try to develop computational methods and try to develop almost rigorous mathematical theories based on what mathematical physicists do. And after that come pure mathematicians who generalize this theory and construct new mathematical theories. For example, the experimental observation that the speed of light is constant in any inertial system. Then theoretical physicist Einstein constructed special and general relativity theories. Then mathematical physicist Minkowski created Minkowski spaces. And then mathematicians created, mostly Poincaré, created differential geometry. After that, it goes back. So applied mathematicians start to use result of pure mathematicians to develop new computational methods. It goes to mathematical physicists, which try to develop their physical theories, and then back to experimental physicists who now learn this physics behind his own discoveries, and based on these discoveries, he can make new discoveries. He can plan new experiments and so on. And then it goes over and over again. So I consider this collaboration between physics and mathematics as excellent, and probably that's why mathematics in physics is so successful. Probably this, but this collaboration is based on ability of people to understand two different fields. Theoretical physicists should understand experiment in order to be able to construct his theory. Experimental physicists should understand theoretical physics in order to apply these theoretical results, and so on. Every neighbor field needs somebody who knows both of them, who can work in two different areas. It's like translators when we talk about different languages. I remember when I was young, it was very popular that the good professional is somebody who knows everything about his field and a little bit about neighboring fields. I think that today it changes. The perfect professional is somebody who knows at least two fields, almost everything in at least two fields, and a little bit about fields around. So, kind of a plan for my talk. Ill-posed problems versus well-posed problems, methods for solving ill-posed problems, inverse problems versus direct problems, Sir Isaac Newton and Mr. Sherlock Holmes and the input to solution of inverse problems, applications of inverse problems, and challenges of inverse problems. Jacques Hadamard defined what does it mean to be a well-posed problem. And at that point, in the middle 50s of 20th century, it was the opinion that the well-posed problems are the problems which should be investigated. The problems which are not well-posed are probably of less interest, of no interest at all. They are mathematically not sound. So Hadamard defined a well-posed problem as satisfying the following three conditions. First, a solution of the problem should exist. Second, the solution is unique. And third, the solution is stable. That is, the solution depends continuously on data and parameters, coefficients, right-hand side terms, initial and boundary conditions. So the first two obvious assumptions are obvious. Third, actually, is very important for application. It says that the small changes of input data should not change the result significantly. And the reason is because these input data are usually the results of measurements. Nobody can make very precise measurements. So every measurement is given with some tolerance, with some possible error. And if this error results a huge error in the answer, then it makes a result almost unusable, right? So in the 20th century, most mathematical papers in partial differential equations were devoted to proving that some mathematical problems are well posed. By the way, as I said, there is a lot of topics, of course, in mathematics behind calculus, and I will choose the topics which were somehow related to my research at different stages. So I also started with proving some kind of the well-posedness theorems for the linear hyperbolic equations. Now, why actually people should study, again, engineering students should study mathematics when there are mathematical experts? There is excellent software now which solves almost any problem in mathematics. This is one example. Let us consider this system of equations. So it's the problem on the level of maybe not elementary, but at least middle school, to solve this system of equations. Students who already took matrix algebra know that the solution, existence of solution, uniqueness strongly depends on the determinant of this system of equations. And the determinant of this system is 1.9, about 2. So it's very good, well-posed problem. And the solution of this problem is x is approximately equal to 1, and y equals 0.05. And now I will change slightly, I will change one of the right-hand side terms. So I introduce the error about 1% in one of the coefficients. Everything else remains the same, just 1% error in the right-hand side term. The small change of coefficient brings about 100% of in solution. I don't remember now what were right coefficient in this system. Maybe it was 100 instead of 10. I don't remember, but sorry for that. So, so this is a phenomenon which is well known in applied mathematics. It's called ill-conditioned problem. This problem is still well-posed problem. However, it's ill-conditioned, which means that the error in data produces about 10,000 times larger error in solution. It's well-posed because still, if the error in the data is small enough, the error in solution will be small from the point of view of pure mathematics. But in applied mathematics, you cannot decrease the error of the data as much as you want. So if it's result of measurements, if it's the error in 1%, that it will remain error in 1%. You cannot make it smaller. And so from the point of view of applied mathematics, this problem is ill-posed. This is another example. This example is at the level of Calc 1. Another very simple example. I hope that I didn't make any mistakes in this case. So let us consider two functions, gx and fx. And the difference of these functions is less or equal than epsilon, because the absolute value of sine is less or equal than 1. So the difference between these two functions is less or equal than 1. However, if we find derivatives of these functions, then the difference of derivatives is 1 over epsilon cosine x over epsilon square. And the derivatives at the point 0 differ by 1 over epsilon. So if epsilon is small number, then if epsilon is 0.001, then the difference could be about 100. The next picture just illustrates it. These two graphs are almost identical. They are graphs of function x and x plus epsilon sine x over epsilon square, but there is a significant difference in differentiation. One danger of our teaching of calculus, the textbooks of calculus are written in order to show the success of mathematics, and every problem has a nice solution, and students who study calculus get the impression that in calculus everything is done perfectly well. Everything is fine. But this example shows that even in calculus, they are even the simplest thing in calculus, like differentiation, such kind of dangerous things can appear. So this is a pure example of ill-posed problem, which is not well posed, because the small perturbation of data as a result give a huge perturbations in solutions. Another very popular example from differential equations is the Laplace transform. And everybody who takes DFQ knows about Laplace transform and knows how successful are applications of the Laplace transform. The inverse formula for the Laplace transform is well known. However, in order to reconstruct the original from the image, integration needed along the vertical line in complex plane. However, in many applications, for example, in applications in differential equations, the Laplace transform is given only on horizontal semi-axis of the real values of P. So in order to get stable reconstruction, you have to integrate along vertical line. But for practical use, we very often need integration along horizontal line, and it's very, very ill-posed problem. So there is a lot of research related today to find stable methods of inversion of the Laplace transform. So this is another example of ill-posed problem. Coming back to the mathematics of 20th century, it was nice. I mean, every next generation has tougher problems. For example, I mean, Isaac Newton was the greatest physicist in the history, but now in elementary school, students can learn about laws of physics discovered by Isaac Newton. Today it seems so simple. Well, then relativity theory comes, which is still not very simple, but I wrote in one of the science fiction humoristic stories, then one or two seniors in high school talk with each other, and one asked another one, "Do you remember general relativity theory?" And he says, "Yes, I think we studied it in the kindergarten." So it's, of course, it's joke, but it's there is some truth in this joke. Every next generation solves problems which are much more difficult than the problems of the previous generation. So I don't want to disappoint our students. It's just some kind of warning that you will deal with much more difficult problems than your professors. Be ready. It's difficult, but it's also very exciting. So the linear problems now become probably history. And now most recent mathematics is related to solution to nonlinear problems. Nonlinear problems are very often, they are ill-posed problems. This is example of nonlinear equation, and this nonlinear equation is well posed. So it's something like cubic parabola. And if you solve it for b equals 0 and b equals 0.1, so b equals 0 is intersection with this line, so it's obviously 0. And the solution, and this line is line y equals b. And so you can see that solution is very close to the solution of the equation with b equals 0. So small change in value of b results a small change of the solution, which is a pure indication of well-posed problem. However, if we consider a different type of parabola, this is something like x cubed or x to the fifth. So it's, again, very nice equation which can be solved easily by hand. But in this case, this is solution for b equals 0, and this is the solution for b equals 0.1. So small change in the right-hand side term b results in a huge change of the solution. So this problem is another example of ill-posed problem, when small change in the data results with huge change in the solution. But at least all these problems have solutions. I remember I love science fiction, so I cite science fiction very often. In some naive story about computer science in probably 30 years ago, there was one scientist who was giving computers problems without solutions. And he was destroying computers. Since computers couldn't find a solution which doesn't exist, they're just burned. Of course, today in computer science, people will laugh on that. But what is interesting, when he was asked why he does it, he said, because there is nothing exciting to find solution if we know that it exists. It's much more interesting to find solution which doesn't exist. I mean, do we need such problems when solutions doesn't exist? This is a problem of mathematical economics. John has $200,000, and John is a Michigan resident. And what does Michigan resident need? House, car, and boat. So the cost of house is $120,000. I'm not very, yeah, it's a very modest house. The car is $40,000 and boat is $60,000. So the problem for John is unsolvable, and that's why he's so disappointed. He doesn't know what to do. So if John asks a mathematician what to do with this problem, what mathematician is going to tell him? Well, probably he would tell it depends on what you want. So maybe a reasonable way to buy house and car and wait a while with boat. Or the problem may be set it this way, to add maximum items with minimal cost, and then he has to buy the car and the boat, or to spend as much money as possible, and then he has to buy house and boat. So, but the bottom line is that mathematics is not enough to solve the problem. You have to know something behind mathematics, something about problem, to be able to solve this problem. Another example about the problems which do not have solutions. These systems are called overdetermined systems. So you have three equations with two unknowns. Obviously, the solutions for the first two equations are 2 and 1. Leszek, I'm correct, right, this time? Definitely, 2 and 1 do not satisfy the third equation. So this problem doesn't have any solutions. So it's also ill-posed problem because there is no solution. And one of the ways to solve this problem is to consider so-called quasi-solutions, or they are also called normal solutions or the least square solutions. And the idea is just take discrepancy of this equation. So the discrepancy is how much AX may differ from B. and try to find x which minimizes this discrepancy. So if system has a solution, then the minimum will be 0. If system doesn't possess any solution, then this function never equals 0, and so we are just trying to minimize it. And it becomes a very nice problem which has a solution, and the solution is called a normal solution. So this is another example. But what I would like to emphasize again, to solve this problem, there is some kind of additional assumption, except of the mathematical statement of the problem. And the assumption is that the discrepancy should be minimized. The regular study of the ill-posed problems started with works of Russian mathematician Tikhonov, who is one of the great mathematicians of 20th century. And it's interesting that he has fundamental results in some areas of pure mathematics as topology, but at the same time, he was a founder of new direction in applied mathematics, direction which was directed to solve ill-posed problems. And the main idea which Tikhonov developed was that in order to solve ill-posed problem, we need some extra information. We have to, now the question is where this extra information can come. It can come only from the nature of the problem. For example, the engineer brings some problem to mathematician, ill-posed problem. Mathematician can do absolutely nothing with this problem because you have to know the engineering nature of this problem in order to understand what additional requirements can be or assumptions can be made. And these assumptions can be made only if somebody knows the engineering side of the story. So basically, in order to solve such type of problems, you need a mathematician who knows engineering and engineer who knows mathematics. So Tikhonov came up with a very useful idea which is used today a lot in many applied researches. I will explain it on a very simple example. If the problem is ill-posed, either because of solution doesn't exist or it's unstable, then as we already discussed, it could be solved by minimizing this function. But if problem is ill-posed, then it's very difficult to find minimum of this function because the function is very plane near to solutions, and so minimization processes do not work well. Tikhonov's idea was to introduce so-called regularization to minimize, instead of this function, minimize function when another term, alpha x minus x bar, is added. So for alpha greater than 0, it means find the minimum of this function, which is as close as possible to the point x bar. And this x bar comes also from the engineering side of the problem. So you are looking for engineering problem. You have some engineering intuition. You can use this intuition to figure out where approximately solution is supposed to be. And then using this information, you choose x bar, and then solve this problem with some value of alpha. And then using solution to this problem, you minimize alpha, you take smaller value of alpha, solve it again, and so on. And so when alpha tends to 0, you get a sequence of solutions which approaches the solution to this problem. Another approach to solving the ill-posed problems is so-called dynamical system approach. And it's the part when I think my contribution was more than probably in other parts of mathematics. And the idea of the dynamical system approach is this. So assume that you have nonlinear problem, fx equals 0. It's probably ill-posed problem. The idea is to construct a dynamical system or ordinary differential equation or system of ordinary differential equations, which starts with the initial approximation point, and when t tends to infinity, it approaches to the solution to this equation. And there are some theorems which show that it can be done under some assumptions on function fx. It's interesting that recently this approach got absolutely unexpected for me application in radiation treatment planning. It was very, for me, it was kind of strange coincidence. I was in Germany with my sister last year, who was getting their radiation therapy, and there was about 1 week period when we were waiting. They said that they need 1 week period in order to plan her radiation therapy. And I couldn't understand why they do need 1 week in order to do it. And suddenly, by email, I got a paper for review at the next day, which was devoted to the planning of radiation therapy. And this, that paper was based on dynamical system approach, and it cited my papers on dynamical system approach. It was so kind, and I got answers to all my questions, why it takes so long and so on. It was kind of strange coincidence. Shortly about inverse problems. So the inverse problems, what we call direct problem, is given the equation, find solutions. And that's what we study mostly in all classes. Again, starting in the second half of the last century, the inverse problems, the theory of inverse problems were developed, and the inverse problem is just opposite. We are given solutions, and we have to find equation which satisfies this, for which solutions are given. There's an opinion that the names are wrong, that the direct problems are actually inverse problems, and inverse problems are direct problems. Because what science actually does, it looks at the results, and it develops theory, right? What Isaac Newton did, he knew how, he had observations how the planets move on the orbits along Sun, and he knew the Kepler's laws, which were results of some type of equations. So he solved the inverse problem, and he figured out what should be the gravitational law, or what should be the equation which provides this result. And those are two people who made tremendous input into the inverse problems. Isaac Newton, who developed physics based on the results of this physics, and Mr. Sherlock Holmes, who was looking at the results of the crimes and was reconstructing crimes themselves. Both are inverse problems. Some applications of inverse problem. in physics, geophysics, astronomy, medicine, engineering, and so on. Okay.